The following is a system of differential equations and its corresponding solutions. Complete questions A through E. Show all your work and/or, if you use technology to get your answer, explain what you did to arrive to your answer. Use the boxes if provided. So they're saying, okay, we can use technology, and we have this right here, which seems to be a first order linear system because we have all constants and we have a first order as the highest derivative, but it is a differential equation in matrix form. And then they're giving us these two x1s and x2s, which seem to be two vectors, functions of time though. Okay. Identify the eigenvalues and eigenvector pairs for the given system. Hint, no math required. Okay, so I just want to step back for a second, and I want to show you that, let's say we have an x prime and a matrix, like we do. X prime is equal to what? It's equal to 2, 1, 1, 2, x. And these are both vectors. Okay. So what can we get from this? Well, we can rewrite this as x prime equals to ax, where A is that matrix over there. Okay. Well, where are we going with this? Well, this really looks like one of the differential equations we used without the matrix part of it. Okay, so why don't we guess a solution? Let's guess a solution x1 e to the lambda t. Now, why are we guessing this solution? Well, because we remember that e to the t, or e to the at, has a derivative that is equal to a e to the at, right? And this form right here is saying that the derivative of whatever is in the x is equal to a constant times that original x. So perhaps this will give us a solution. So let's try to find what x prime would be. Well, we're assuming x1 is just a constant, so it's going to stay in front, and nothing's going to happen to it. While the derivative of e to the lambda t, the lambda will go in front, and we'll have this. Okay, so now if we substitute that back in, we're going to have e to the lambda t here, and a, and now for our x, we said our x is x sub 1 e to the lambda t, which means that this is going to cancel out, and that we're going to have a x prime equals, I'm just flipping, equals to this. So this, you should recognize it. We usually have it with v, but this is the eigenvalue problem. So if this is the eigenvalue problem, then that means that this can be true perhaps. And it can be true if we're able to do this. And there's other videos where I explain more in detail why we put that identity matrix there. But if this determinant is 0, then x is a solution. The x1 that we guessed. And if that is a solution, then what would be the coefficient in front of the t? That would be the lambda. And that would be the eigenvalue. So in this case that they give us, what are the eigenvalues? Well, it's going to be the coefficient in front of the t. So we're going to say that the eigenvalue here is 1, and that the eigenvalue here is 3. Okay, and now what else are we going to do? Well, now we want to find the eigenvectors. And this is the eigenvector. See, we had it right here. So in our guessed form, this was the eigenvector. Eigenvector. And this one, this lambda, was the eigenvalue. So all we have to do is say, okay, with the eigenvalue of 1, we had the vector -1, 1, and with the eigenvalue of 3, we have the vector 1, 1. And that's going to be part A for this problem. Part B says use the Wronskian to show that the solutions are linearly independent. So the Wronskian for vectors is going to have is going to be the determinant of the matrix that has our two solutions, x1 and x2. And I don't need a comma if this is a matrix. Okay? So what are they? Well, it's going to be the determinant, or I can just write the vertical wall of our two solutions, which are this and this. If I distribute that exponent that's in front, that exponential that's in front, I'm going to get negative e to the t and e to the t for x1. So negative e to the t and e to the t. And the other one is going to be e to the 3t, e to the 3t, e to the 3t, e to the 3t. Okay. No, we want the vertical. There you go. So now what do we want to do? Now we want to find the determinant, because that's what these vertical brackets indicates. And so we're going to have negative e to the t times e to the 3t minus e to the 3t e to the t. Well, what is this? Well, we can leverage the properties of exponents and add the exponents here. And it's going to be t plus 3t, which is going to be 4t. So negative e to the 4t. And here as well is going to be negative e to the 4t. Negative e to the 4t, which is negative 2 e to the 4t. In any case, this is not equal to 0, which means this is just a way to say that the conclusion of the previous process is that the solutions x1 and x2 are linearly independent. Okay? And now that we have this, we can form a general solution with the superposition principle. So with the superposition principle, we have that the general solution x is going to be the sum of x1 times some constant and x2 times some constant. And given that those were our solutions, we're going to say that we're going to have c1 times negative 1, 1 e to the t plus c2 and 1, 1 e to the 3t. And now verify that the solutions given are actually solutions to the system, to the given system of differential equations. Now we have to do it twice because we have two solutions. So let's rewrite our system. We have x prime is equal to this matrix, this 2 by 2, 2, 1, and 1, 2. Okay, 2, 1, and 1, 2, multiplied by, well, the first time it's well, let me do that later. Multiplied by x. And these are both vectors. And now what are we going to do? Well, we have x1, so I'm going to copy the solution x1. So we have x1 is equal to, doesn't have a constant there. It's going to be equal to 1, 1, or negative 1, 1, right? E to the t. And x2, and these are vectors, x2 is going to be 1, 1, e to the 3t. Okay. Well, so now that we have this, what are we going to do? Well, if this is a solution, then that means it must satisfy this equation. So I think of this kind of like algebra where you plug in the value of the variable to check if the equation holds. But these are special variables because if I know this variable, I know this one too, so they're related. And so how do I find this one? Well, it just tells me right there. It's the derivative of the original value. So I'm going to find the derivative of both of these, and it's going to be what? Well, the vector is a constant, so it's really only what's in front of it that matters. And in this case, it's e to the t. Well, the derivative of that is just e to the t. How convenient is that? And then we do the same for the other one. Well, this one's going to have a 3 in front, so it's going to scale the vector by 3. So now we plug everything back in. So we want to plug this over here and this over here. And then on a second round, we want to plug this over here and this over here. And we want to see if this equation actually holds. So let's go with x1. For x1, we have -1, 1, e to the t. And then I'm actually going to distribute the e to the t inside because I think it'll make it a little bit easier for us. So that's going to be negative e to the t and e to the t. And on the other side, we're going to have 2, 1, and 1, and 2. And here, we're going to have negative e to the t, e to the t. Now, the way I like to think of matrix multiplication is this way, especially when I'm dealing with vectors and a matrix. I like to do it this way. So I'm going to rewrite the left-hand side. And the right-hand side is just going to be negative e to the t multiplied by the first vector of the transformation plus e to the t multiplied by the second vector of the transformation. And then, as you know, you have to scale each component of those vectors by those scalars. So we're going to get negative 2 e to the t plus e to the t and negative e to the t plus 2 e to the t. And this is a matrix, remember. This is still a matrix. And don't get confused by the aspect of this matrix. That has to have an equal sign. Because you may be thinking, hey, this is a 2 by 2. Well, actually not, because you see how there's operations in between these. So it's really only a first entry and a second entry. This is a 2 by 1, which is what you would expect because you had a 2 by 2 and a 2 by 1. So the outside dimensions tell you what the result dimensions would be. So here we'd have negative 2 e to the t plus e to the t. That's negative e to the t. And then the bottom is going to be negative e to the t plus 2 e to the t, which is just e to the t. Okay, which is the same thing as negative 1, 1 e to the t, which is what we started with, right? This was our original solution. So yes, the first one checks. And now we're going to do it a little bit quicker maybe so that we can save some real estate. Or maybe I can put it down here. Let me see. I can put it down here. For x2, what is it going to be? Well, I'm going to distribute that exponent. I'm going to get negative e to the t. Hold on. Don't make any mistakes. Look at this one. It's going to be e to the 3t, e to the 3t is going to be equal to the matrix 2, 1, 1, 2. And here we're going to have, instead of e to the 3t, we're going to have 3 e to the 3t. Because that's our derivative, 3 e to the 3t. Okay. Well, now we do the same process. I like to put e to the 3t here, and then multiply it by the first vector, and 3 e to the 3t here, and multiply it by the second vector, which results into 3 e to the 3t times 2, which is going to be 6 e to the 3t, plus Plus 3 e to the 3t, and I noticed that we might not get the same result, so there might be a mistake going on in there. Let's see, where are we finding the mistake? And here at the bottom, we're going to have 3. Nope. We're going to have, instead of 6, we're going to have 3 e to the 3t plus 6 e to the 3t. And so here we see that we are getting 9 e to the 3t and 9 e to the 3t. So x1 is a solution. X1 is a solution, but x2 isn't. Now, if I made a mistake, I apologize, and it might be a solution, but I'm gonna check it with the computer and see if indeed it is a solution or not, just to see if I made a mistake or not. But this is the process. All right, make sure to put in your documentation statement if you're watching this for this particular class. Make sure to document the help you received. All right, I'll see you next time.